First talk will be by David.
Thank you for the introduction. So this is joint work with Mark, who's a PhD student at the University of Edinburgh, and actually did most of the coding. In case you're interested in seeing how it works, it's on his GitHub, so you can run everything. Yeah, I'm at the University of Edinburgh and Vega protocol, but this has nothing to do with Vega in the sense that, it's just us trying to see what's happening in the blockchain world and, explore it. And unlike some of the talks we've seen already that are based on real chain data, this is purely a simulation exercise. So there is, no real data was harmed in making this talk. So constant product markets, I suppose we're getting to the point where this is so well known that we shouldn't need slides on saying what they are, but they're sort of they're an example of a more broad class of constant function market where basically price is set by keeping a certain quantity invariant. In this case, it's this product of two reserves, and there is I will advertise Tarun's paper, which probably everyone has read now, on analysis of the Uniswap market, and sort of they have a number of desirable properties. The main one being that they set prices automatically, as the name automated market makers suggest. They're relatively intuitive once you spend a bit of time thinking about that. So sort of, the main properties is that a tiny trade would trade at the ratio of the two assets, so you can think of the ratio effectively as the price. If you decide what your numeraire asset, your slippage depends on the trade size, and the bigger the trade, the bigger the slippage will be. And typically there is a fixed fee that's fixed at pool creation, and we will focus on the fee a bit more in a moment. But as a market maker or as a liquidity provider, if you lock money with the protocol, then you don't really set the prices, which for me, coming from more traditional limit order book based world, is kind of unintuitive, and it's one of the features that I wanted to explore. And so somehow, if you assume that there are informed traders in the world who know better than you what the asset price should be, then they're basically always at an advantage against you as the person who has the money locked in the pool. All the trades are effectively arbitrage there. They're making money, and the fee should compensate you for that, together hopefully with some sort of dumb non-arbitrage order flow. Right, and so just to belabor the point, the reason why you're always arbitrage is that the price only changes when a trade happens. Unlike if I'm providing liquidity in a limit order book, I can simply reprice all my limit orders, the liquidity is there, but the price at which the next trade will happen has changed. So why are they suddenly popular? They are not a new thing. That they're, I think, from 60s or 70s, or certainly there are mentions of literature of them 50, 60 years ago. They're popular because they're perfect for relatively weak and slow computing environment like Ethereum, and also there are you've got no storage requirement for them. You're basically storing couple of bits of numbers. It's very cheap, so they're extremely popular now. And the question is, do actually the liquidity providers make money? And so there are some studies. So the graph at the bottom is showing it's a little bit hard to read, but the blue is the fee income, and orange is the impermanent loss for a bunch of popular pools on Uniswap, I think. And it looks like the liquidity providers are quite often losing money. Why? are people willing to accept that? I think partly in the last year it was because you typically had one sort of stable coin and another risky asset, and because all the coins were going up like mad, you didn't quite see that you're losing money in this business. You might have made more money if you just held the coin and didn't have it locked up for liquidity. But and so some people are making money. This is the MEV revenue, and this slide throws these two pictures together. It's not trying to imply that MEV is the reason why the liquidity providers are losing money. It's not. It's just on the same slide. Okay, so why would a liquidity provider lose money? Well, if you're running on an order book, you would say, well, you've got a bad trading strategy, right? If you're not making money out of being a liquidity provider, you shouldn't do it. You should do something else. Here you don't set prices, so in some sense, it's the protocol or the curve that determines whether the liquidity provider will on average make or lose money. And so what does sort of classical market making theory have to say on the topic? So we went through some papers, and I list kind of 3 models named after people, some of them very famous economists, and the last one is based on stochastic control. And there are models in stochastic control where the volatility matters. There are ones where the volatility doesn't matter. That's why they're kind of twice. But sort of the economists who, in this case, really, they're economists in the best sense of the word. It's not this macro hand waving. This is really all the models are very rigorous, trying to understanding what an optimal strategy for market makers in certain situations should be. And the models are very different, but in all these, all these 3, basically one way or another, they say that, if the underlying asset you're trading has got large volatility, then you, as a market maker, would like to set bid and ask spread that is large. In constant product markets, you can't set, bid and ask. That's not what's supposed to compensate you from the loss incurred by informed traders. What is supposed to do that is the fee. So somehow, those 3 models would suggest that, for assets that are highly volatile, you want a higher fee or a different curve, sort of, whether you do a higher fee or do some kind of different curve in your constant product market is somehow irrelevant. But one way or another, what you're doing probably is somehow related to the volatility. And so I don't think I want to go into the detail of the model. It's better to read in one of the books that we say reference in the original papers, or in the book we reference in the paper. But typically, you get something like this. So if mu is the fair price, if the market maker is willing to buy it, then there will be some impact from volatility, which is the sigma squared, something from risk aversion, which comes from utility maximization, and how the game is set up. And in this case, it's basically saying that if you have more market makers, then there should be less of that penalty in the fair situation. Okay, and this, maybe I won't talk about too much in detail about this, but the idea is that in all these stochastic controlled models, you just describe things like how does the mid price move, and then maybe you describe things like the way that you assume that orders arrive, and then you come up with some sort of performance criteria which you're trying to optimize, and that will tell you how you should post your bid and ask. So typically, in these things, the market maker is penalized for holding the inventory of what they consider a risky asset, which is this Q. So there is a penalty for that. It leads to relatively nice control problems because they're sort of linear quadratic type, so they typically have relatively closed form solutions. And then so what happens is, that if you're very short of the risky asset, then you can see that you set the ask price relatively far away from what you would think is the fair price. So that's the kind of thing that you get here. Okay, so that's kind of that was all of that was the background, and now we get to the simulation, to the agent-based simulation that we did. So it's based on the assumption that there is a constant product market. There is another liquid exchange, which can be based on limit order books. It could be another pool, and there are effectively two agents in our model: the LP, who just puts the money into the pool and then leaves it there, doesn't do anything. So you don't even have to think of them as an agent, because they're not taking any actions. And then there is the other agent, the arbitrageur, which sort of trades on the liquid exchange, trades against your pool, and tries to make a profit. And so the agent is just solving a fairly typical stochastic control problem. This is what you have written down here is the formulation for discrete time stochastic control, allowing randomized strategies. If you have a problem like that and you want to solve it with pen and paper, well, unless things are convex and linear, pretty much you're out of luck. You're not going to solve it with pen and paper. If you do know the environment, in other words, you do know all the transitions of your system, and you know exactly the reward function, then you are in the world of stochastic control that goes to Bellman in the 50s, and you can run policy iteration algorithm, and policy iteration algorithms are known to converge under mild assumptions, so you're in a good shape. Oh, and I see I've misspelled Galerkin. Never mind. Right, and if you do not know your environment, in other words, you do not know the transitions and the reward function, then you're in the world of reinforcement learning, and there the situation is a bit more complicated. You generally don't have proofs of convergence of these policy gradient type algorithms, but the reinforcement learning people know that they work. So, and they do work. It's like, okay, they do work. Can't argue. It's not convex optimization, and yet it works. Fine. And so we could have really chosen either of these approaches, but we wanted to do it in the reinforcement learning setting, because then we don't, then the agent doesn't have to know. For example, you don't have to tell the agent what the slippage will be. It simply learns from the environment. And so if you do this stuff in the reinforcement learning framework, then you're setting something up which can be easily extended and is much more flexible if you then want to do more complicated things. You don't have to tell it, one of the components of the state of the system will be the price process. You don't have to tell the agent what the price process is, etc. So you can have more fun. That's the message. You can have more fun if you use reinforcement learning. And okay, so this is the algorithm, and basically what you want to do is you say, I approximate the optimal policy, which is just some density function from which then I draw my actions. I use one parametrization for that. Again, that could be, you can do something linear like Galerkin, you can do a neural network, and then you approximate the optimal value with another, parametric function. The reason why in reinforcement learning and in many things the neural networks are so popular is that they cope extremely well with high dimensions. And in fact, you do have now mathematical results that for the type of objects such as appear here, you can actually efficiently approximate them even if X is very high dimensional, which is kind of a big deal, because if you know the term curse of dimensionality, that actually comes from Bellman, from when he was trying to solve control problems. And the problem is, you know, if you do something that's not based on a neural network, then let's say you do something naive, you want to discretize the 0-1 interval, you chop it up into pieces, fine, you have n pieces, and you can ensure that, you know, if you take step delta, then there is no gap bigger than delta. If you want to do that in 2 dimensions, you've got n squared. If you want to do it in 3, 5 dimensions, it goes pretty fast, and you run out of memory and you run out of time. And neural networks somehow, in many cases, don't have that problem and can approximate various objects like solutions to certain PDEs and value functions for control problems without being hit by the curse of dimensionality. So that's why you may want to use neural networks in this setting. And then sort of the algorithm is fairly easy. You know, you sample from the states of the system. You know, you let the agent choose their strategy. You then say, okay, if I did that, how would I improve my approximation of the value function? In other words, I do a gradient step updating the value function, and then, you know, I do a gradient step updating my policy, which is simply saying, you know, once I have a good estimate for my value function, then this is sort of hiding the Bellman equation or the Bellman principle, which says that in these stochastic control problems, here it looks like, you know, you're maximizing over an infinite time horizon, but in fact Bellman principle tells you that you can maximize over 1 step plus the value function of the future state. So that's the trick. You run this, and then, you know, maybe it converges, maybe it doesn't. And it turns out that it does converge. So on the left, it's the agent changing direction. So this is not expected to be stable. But here on the right, you've got the approximation of the value function, and you see that converges as you train. Okay, and then here is a, you know, typical run of the trained agent and the pool and the external price, and you see, you know, it sometimes chooses to trade when it's a good deal. It's making money, and this is a known result that, you know, if people try to arbitrage these constant function markets, then they can follow the external asset price very well. So that's, you know, that's just a sanity check that things work. And so now is effectively the punchline. So here we have density plots on, here I have the external price volatility. You know, the shading indicates the gain of the market maker, or in other words, the impermanent loss of the pool. And, you know, you see that as your volatility increases, and if the fee is low, then the impermanent loss, you know, is high. And then on the right hand side, we just have the variance sort of to see whether it's, you know, whether this average value is representative or not. And you see, especially in the region that you care about, that, you know, there is large variance, but you know, on average, the pool liquidity provider suffers from this impermanent loss. Okay, and this was sort of our first stab at this kind of modeling. You can do all sorts of extensions to what we've done. Some of them are listed below, and I think, okay, conclusions I walked through. Yeah, there are the references, and that's me. Thank you.